All right, here we go. This video, just one topic and really just one problem. I think it will be that simple for this video. But the topic is the slope of a curve, and I put in parentheses in polar coordinates. So if you take Calculus 1, you learn about the concept of the slope of a curve. But, at this point in Calculus 2, we're dealing with polar coordinates. So let's just say that the curve's given in polar coordinates. All right. Now, I won't derive this formula, at least in this video. I'm not going to do it. I'll just give it to you, and we'll put it to use doing a problem. Okay? So the curve is going to be r as a function of theta in polar coordinates. Some kind of equation where theta goes in and r is calculated. Okay? All right, that's what I mean when I say r is a function of theta. Something like, r is equal to 6 times cosine theta. Something like that. All right? Now, the slope of the curve will be calculated according to this formula, which I won't read to you, but there it is. And when we see dy dx, that's the Leibniz notation. But, that's the slope of the curve, the instantaneous rate of change. I guess in rough terms, you could think of this as rise over run, okay? So that's why part of the reason why we use that notation. But there it is. That's how you calculate the slope of the curve. Now, I wanted to give you, as an example of this curve, which happens to be a circle with its center on the x-axis. It has a diameter of 6. It has a radius of 3. That center point is at 3 on the x-axis. And graphing that and knowing what that is, that's a topic I've addressed in another video. All right? But let's say that I give you that, and I have a few points of interest, like there's this point 3 root 2 for r and 45 degrees for theta. Can you tell me the slope at that point? Or this other point, 6 for r and 0 for theta. Both those points are on this circle, and they satisfy that equation. But before we calculate the slopes at these points, what's the formula for it? What's dy over dx, okay? So let's do that here. All right. So I've got my formula this time, okay? And I'm going to put that r being a function of theta, this time is r is equal to, what was it, 6 cosine theta? Okay. And so that's f of theta right there. And f prime theta, by way of use in that formula, is going to be negative 6 sine theta. Okay, so that should be it. That's all we need. So here goes. Dy over dx, our instantaneous rate of change, our slope of the curve. Here it is. Just a matter of putting it all together. So f prime theta, this part, that's going to be negative 6 sine theta. Okay, and then times sine theta plus f of theta, that's this thing right here. So 6 cosine theta times cosine theta. All right, that's the numerator. And then underneath that, f prime theta. So that's going to be negative 6 sine theta. Okay, cosine theta. And then minus f theta. F of theta is 6 cosine theta. So I get 6 cosine theta sine theta. All right, so that's initially what I get, which that can be reduced quite a bit. Okay, so first of all, I could factor out a 6 from the top and the bottom, and I could cancel it. So all we're looking at up here is cosine squared minus sine squared. That's it, okay? So cosine squared theta minus sine squared theta. All right, that's that top part. That's what we got. Down here, now given that, say, I factor out the 6's and I cancel them, I'm going to get negative 2 sine theta cosine theta. Combining some like terms, again, after I factor out the 6 and cancel it. Now, these are both double angle formulas. All right, now, and I know that, you're not going to remember every identity that you've ever seen, but this one, I hope it at least would look familiar. This is going to be cosine of 2 theta. Okay, Yes, there's an identity. It's the double angle identity for cosine. It says cosine 2 theta is cosine squared theta minus sine squared theta. And this is the double angle identity for sine. I'm going to carry that negative to the front over here, and that's going to be sine 2 theta. And again, that is true, that sine of 2 times theta, sine of twice an angle, is 2 times the sine of the angle times the cosine of the angle. Those happen just by coincidence, the double angle formulas for sine and cosine. So I will say that my final answer will be negative cotangent 2 theta. There's my formula for the slope of that curve. Okay? I mean, you got the formula, right? You plug everything in. But we should reduce as much as we can and recognize identities when we need them. Even if we have to look it up, you can go look it up if you're not sure. But I hope that those look familiar. Okay, they are the double angle formulas for sine and cosine. So I'm going to do this. My first answer here, dy over dx is negative cotangent 2 theta. That's the formula that will give you the slope of the curve. Okay, at some point indicated by the angle. What's the slope of the curve at this point? Right there, okay? Now, I drew this perfect circle, and I got my protractor out, and I put that point right at 45 degrees, okay? And yes, if you do the calculation, 6 times cosine 45 degrees is 3 root 2. It's on there. What do you expect the answer to be? Well, we maybe expect the answer to be 0. It's flat up there. At that point at the very top, which is where this point is, it is flat. It has a slope of 0. So we would expect that when we do the math there, that we get 0. Okay. So anyway, so let's see cotangent. Let's do it like this. Dy over dx, okay, is negative cotangent 90. Right? There we go. So we got to do, put the theta in. Theta for the point's 45 degrees, double it, I get 90. Okay. And sure enough, cotangent of 90 degrees is 0. Okay. So I get the negative of 0 or 0. So it's flat. At that point right there, it's horizontal. In case you didn't know that horizontal meant flat. All right. So that, I calculate that. Like I know how to do cotangent of 90, and I get 0. And it's consistent with what I'm seeing, that right there at the very top, it's flat, it's horizontal there. Okay, what about this one? Calculate the slope at the point 6 and 0 degrees. Well, that's this point. Well, at that point, it would be horizontal. Okay, and so the slope would be undefined. All right, so let's see. If I do this, dy over dx at that point where theta is 0 will be negative cotangent 0 degrees, right? Technically it'd be negative cotangent 2 times 0, but 2 times 0 is 0. Well, cosine or cotangent of 0 is undefined, okay? And I'm not surprised about that. If I calculate cotangent of 0, it's undefined. Well, because the slope's vertical, so it would have to tell me something like that. Like a vertical line has undefined slope. So it's flat or horizontal at this point. It's vertical at this point, okay? And I wanted to have one more point just to round things out. What about the point where theta is 10 degrees? Well, so like just to have some perspective on this, I mean, oftentimes there's not a whole lot to just doing the math. So 10 degrees, that's going to take me about right there, okay? So at that point, theta is going to be 10. It turns out that with some rounding, let me see how much. So what's 6 times cosine of 10? So it's about 5.9. So this point's about 5.9 for r and 10 degrees for theta. Then it would be like, I don't know, about that steep right there. See, I'm putting my pencil, my pen, that'd be the rise and the run, okay, if I align it with the circle. So you'll get some like negative slope, right? It's going, I don't know, fairly steeply down and to the right. All right, so that will be the slope at theta is 10 degrees, or at this point right there, where r is about 5.9. Well, so let's see. That would be this dy over dx is negative cotangent of 20 degrees. My formula is dy over dx is negative cotangent of 2 theta. If theta is 10, then I'm doing negative cotangent of 20. So, well, let's see. What is that? I need my calculator to do that one. That one is negative 2.7. So with some rounding, it's about negative 2.75 or so. Okay, and that's not vertical and it's not horizontal. It's somewhere in between. So like you're right here, it's how steep it is. Down about 3/1. Okay, so when I'm looking right there at the curve, like maybe on a macroscopic or microscopic scale, looking really close so it looks like a line, then I'm gonna see something like this, right? And just looking from point to point, I'm going to be going down negative 2.75 and to the right 1. That's what I mean by this being the slope, because that's what slope is, of course. All right. So you can imagine that, right? I want you to have like some kind of context for the numbers, but yeah, see that? There's my tangent line to the curve. Down negative 2.75, right 1. That's what the curve is like right there. Okay, so we got our slope formula for a curve in polar coordinates. All right, we've got an example. Reducing this might involve trig identities, but these are just calculations. Okay, hopefully you can tell that every single answer I got is consistent with the way this curve looks to start with.